Hi again. Now the chapter that we are in, analysis techniques in frequency domain, we mentioned the serial parallel equivalent circuits and how we use these equivalent circuits in the analysis, and source transformation equivalent circuits, how we use these equivalent circuits in frequency domain analysis. Now we came to general analysis techniques. There are three techniques that we know. One of them, if we go in, we will see it better. Classical method, node voltage method, and mesh current method. We will be examining this classical method right now. For this, I will transfer to whiteboard. Open more. Okay, and this. Here we are. The circuit given to us is always the time domain circuits. That is the circuit given to us. So when you transfer to frequency domain, the circuit parameters are going to change. How it is going to change, I just explained to you. Here you are, there is one independent voltage source. This is time domain definition relation of this, isn't it? The Vs, that means voltage of this independent voltage source equal to that sinusoidal function. So we've got to transfer this function to its phasor. How we are going to do it? Vs, so let's make the color black. So Vs, this independent voltage source phasor is equal 10 times magnitude e to the power j, the angle, it is 30. So this is that. So this is time frequency domain circuit, omega domain, let's say. This is time domain circuit. Make it a bit better. So this is given to us in the exam. This will be given to you, and then you're going to transfer this circuit to this one, of course. The next thing is to transfer these element parameters in time domain to the impedances on the omega domain. How we are going to do it? The resistor resistance or impedance doesn't change whether it is time domain or omega domain, so this 10 goes to less 10. For this resistor 20 ohm, transfer to that 20 ohm. But for the inductor, the impedance is ZL, impedance is J omega L. J omega is this. That is the angular frequency of the independent voltage source. It is 100. So 100 times L. L is 100 millihenry. 100, that 100 milli is 10 to the power minus 3. So this gives me, that's 4 zeros. So it is J10. So this is this 10J. This is inductor's impedance. What about the capacitor impedance? It is ZC is equal 1 over J omega C is equal, if we move that J upwards, it is minus J 1 over omega C. So minus J 1 over omega was 100. C is 100 microfarad. That's 100. Micro is 10 to the power minus 6. So we've got 4 zeros here. Minus 6 makes it minus 2. If we move it upwards, it becomes minus J 100. So this is this one. So when you transfer the impedances and the independent sources, we end up with a new circuit. This is the circuit corresponding to this time domain circuit. This circuit is omega domain circuit. From now on, if we are using the classical method, we are going to write any equations, any unknowns. So we could, let me move that one now for the other steps. So NE, number of elements in this circuit is 5. 2NE is equal to 10. So I will be writing 10 equations and end up with 10 unknowns. So let me write the independent Kirchhoff voltage law equations first. Since there are two meshes here, there are two independent Kirchhoff voltage law equations that we can write. So for writing these mesh Kirchhoff voltage law equations, we've got to choose a loop direction. So I have chosen this one first, and for the second loop I have chosen this loop direction, and this element current is I1, is the reference already been chosen. I will be choosing now a current reference for the resistor like that. You know that you could choose these references as you like, but I have chosen them as clockwise. Okay. Now we are ready to write the Kirchhoff current law equations, and we know that altogether this is going to be just two equations because we have two meshes. For the first one, since the loop reference and the 10 ohm resistor references are the same direction, so it's going to be plus V10, and this loop direction and this 20 ohm resistor current directions are the same, so plus V20 is equal this independent voltage source voltage, that is 10 to the power J30. Why its sign is positive on the right hand side? Because if you were writing it on the left hand side, this element current reference is downwards according to passive sign convention. So if you write this voltage, this element independent voltage source voltage on the left hand side, this direction, loop direction, and this element current direction are opposite to each other. Therefore, if I were writing this element voltage on the left hand side, it were going to be minus. So I moved that minus to the right hand side, that minus became plus. So that's the first mesh Kirchhoff voltage law equation. For the second equations, we are going to write it for the second mesh. So you might call it this is first mesh, and that is the second mesh. So for the second mesh, minus V20, because this direction and this direction opposite to each other, and the other voltage is the voltage of the inductor, VL. So these are all phasors. So we are in frequency domain, and we are writing the frequency domain Kirchhoff voltage law equations in phasors form. So VL directions are the same. For the VC directions are the same, plus VC capacitor voltage phasor equal to 0. So when you wrote all these equations, so you could do some checks for that. How are you going to do the checks? If you look at the first mesh here, you've got three elements. So you're going to write three in your equation. There should be three terms. 1, 2, 3 terms we've got. For the second one mesh also we have three elements. So there are three terms in our equation. If these were not the same, what I mean is if the number of elements is 5 in a loop, and you write three terms in your equation, that means you made a mistake. So what about the Kirchhoff current law equations? Make it a bit different color. Kirchhoff current law equations. How many of them we've got here? So this is one node. That's another node. This is third node. And this is fourth node. So if it choose this as ground, so we've got three nodes, independent nodes here. For each node, I am going to write a Kirchhoff current law equation. So the total number of independent current equations that I am going to write is equal to 3. So for the first node, both of the currents are coming out of the node. Therefore, the IS plus I10 is equal to 0. Both of them coming out of the node. So for the second node, that's 1, 2, 3. This current is towards the node minus I10 and plus I20. So this current coming out of the nodes, that's why it is plus. This current also coming out of the node plus IL is equal to 0. For the third node, so this current IL is towards the node minus IL, and this is coming out of the node plus IC is equal to 0. So these are the three Kirchhoff current law equations, independent equations that we wrote here. So what is left is five equations related to the definition relations, since we've got 5 elements here. So what are those definition relations? It's going to be 5. We're all going to know that. So let me write those definition relations in different color. So the first one is Vs is equal 10 to the power e to the j30. That's the definition relation of this element, isn't it? This one. And for resistor 10 ohm resistor, V10 is equal 10 times I10. And for the other resistor, V20 is equal 20 times I20. For the inductor, VL is equal J omega L E L. J omega L is equal, we already found here, 10J IL. And the VC is, this is the impedance, minus J100 IC. So we've got five definition relations here. The total number of equations we wrote here is 10. The total number of unknowns is 10 also. So that's the classical method. Since the number of equations is equal to the number of unknowns, so there is a unique solution for that. Let's transfer these 10 equations to a matrix form now. So I will be using this matrix form. So that's one of them. And so we've got 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for this matrix here, and these are the unknowns column matrix, and is equal to known column matrix a bit here. So I'm not going to go in details. So if this matrix is going to be like that, anyway, let me write it. So it's not so that difficult. Oh, I made a mistake. It is going like this way, this way, this way, and this, this, and clear those. Okay. So how are we going to transfer these equations to the matrix? It's easy. So let me write these unknowns here. Vs, Vs, V10, V20, VL, VC, and then IS, I10, I20, IL, IC, capacitor current. So if you this is the first equation that I would like to transfer to this matrix form. So the first element here, 1, is equal to 10 to the power e to the power 10 times e to the power j30. So if I write the right hand side this value here, and 1 here, rest of them 0, the first multiply this one with this row matrix, you're going to get Vs is equal to 10 times e to the power j30. This is that one. So for the second one, V10 is the second one, so the first one is 0, the second one is 1, is going to be 10 times I10. I10 is the fourth one from the left, the last one, so 1, 2, 3, 4, so minus 10, 0, 0, 0, 0, 0, 0, 0. So if you write this one here, V10 minus 10 I10 is equal to 0. So that's the equation, isn't it? So that is the second one, Vs. The rest of them 0. You don't see them. For the I10, the coefficient is minus 10. That's minus E10 is equal to 0, is equal to 0. I wrote the second equation now. That's the second one. Third one, V20 is the third one, 0, 0, 1. And if you consider the similarly that what we have done here, it's going to be minus 20 I2. I20 is third one, 1, 2, 3. So minus 20 here, 0, 0, 0, 0, 0, 0 is equal to 0. That's the third equation. Fourth one, VL is the fourth one, 0, 0, 0, VL is 1, minus 10J, that is IL, the second one from the last, so this is 10 minus 10J here, 0, 0, 0, 0, 0. So this is the fourth equation. Fifth one, V5, 0, 0, 0, 0, 1. The last one is minus 100J. So 0, 0, 0, 0. Now these 5 equations here that I wrote is these 5 equations in here, definition relations. Now I will be writing these Kirchhoff voltage law equations now. Let me write them in different color. So V10 is the second one, so V10 is this, the coefficient is plus 1 here, and the other one is V20, that's the third one, and the coefficient is plus 1, is equal to 10 to the power, so 5, that's the sixth one, 10 to the power A, J30. So the rest of them 0, isn't it? So this is the equation corresponding to this one. This one, minus 20 is the third one. 1 to minus 20. Coefficient is minus 1. VL is the fourth one. The coefficient is plus 1 here. And VC is coefficient is 1, 1, 0, 0, 0, 0, 0, and 0. So this equation is this one. So I transfer this equation to this matrix now. Let's do the last Kirchhoff current law equation transfer to a matrix form. IS is the sixth one, isn't it? 1, 2, 3, 4, 5, 6. IS is plus, and minus 10 is plus. Both of them, the coefficient that's plus 1. So the 0, 0, 0, 0, 0, 0, 0, 0, 0. That's this one. So minus 10 is the fourth one from the left. 1, 2, 3, fourth one, minus 1. Minus 1, plus 1 for I20, and plus IL for inductor. So that's the one. Equal to 0. So that is the second one. So that's this one. The last one, minus IL. So this is minus 1 and plus IC. Rest of them 0. And that is 0. So altogether, so this I forgot to put zeros here. So 2 more zeros. Now this format is the linear equation format, isn't there? So I can say that this is now. Is there any other color left? Maybe not. Okay. So this is this form, linear equations. This is unknown matrix, which is this. This is square matrix, or the coefficient matrix is this one. The dimension of it is 10 times 10. And B matrix is the known matrix here, is a column matrix. And in this matrix, we've got all knowns here. The solution is going to be X is equal inverse of A multiplied with B. So that is the classical method by using the phasors method. So at the end in here, what we are going to find, so these all unknowns, the 10 of them, are the phasors, either voltage phasors or current phasors of all the elements inside the circuit. So if you look at the A matrices, there are many zeros there. So in general, you can say that the number of entities, different number of entities that you can see in the matrix A is zeros, plus ones, minus ones. These are the coefficients that you see in the Kirchhoff current and voltage law equations. In this one, we are going to see the impedances as well, since these are the impedances of the elements where we see in the definition relation. So in this part of the matrix, we've got zeros, ones, and minus impedances. So the conclusion that we can get out of this, the first one is this. By this method, you can find all the elements, current and voltages, but in order to find that, you've got to get the inverse of this A matrix, 10 times 10 dimension matrix. Not easy to do. On the other hand, you might consider that this 8 matrix has got many zeros in. Is there any alternative way solving less number of equations but to solve the circuit? These are the other methods that we're going to examine. These are the node voltage methods and the mesh current methods. We finished them up. So let me move to Prezi once more and show you That is the one. If we go a bit inside here, so it is only written here the 10 ohm resistor current and the 20 ohm resistor current, but the solution that all must consider all of them is not written here. That's the end of this video then. How we are going to do it.